Thank you, and many thanks, of course, Tunke, for your very nice invitation and for putting together this nice event. Yeah, good morning, everyone, and thank you for being here. As you heard, my name is Emilio Martínez-Pañeda. I'm an academic at Oxford. And today I want to talk about, maybe I can. Yeah, I want to talk about a different problem, hydrogen-assisted fracture. I'll just link to some of the talks that we've seen yesterday and today as well. And I want to talk about how we have developed, I would say, mechanistic coupled electro-chemo-thermo-mechanical phase field-based models to be able to predict this hydrogen embrittlement or these hydrogen-assisted fractures. But before I get into this, just because it's an extended talk, I think I'll spend 1 or 2 minutes motivating the background for this problem, for the sake of those of you that are not working on it. So, hydrogen-metal interactions have been of interest for a very long time because hydrogen is basically everywhere. And as you will see later, it significantly degrades metals. And you have probably seen in the news that there's a significant interest in hydrogen these days. And this is due to the fact that it has the potential to decarbonize many applications and sectors, including some that are known to be very difficult to decarbonize, such as aviation or steelmaking. We cannot think of any other alternative in that case. So it seems that we are going to have to deploy over the short term a hydrogen energy infrastructure. And that's going to be a challenge because we know for quite a long time that hydrogen embrittles metals. And again, this is something that we know for almost 150 years ago. So you see here, this is a paper by Johnson published in the Proceedings of the Royal Society back in 1875. And you can see that he talks about some remarkable and extraordinary decrease in toughness and breaking strain in iron and steel in the presence of hydrogen. And in those days, you rarely see words such as remarkable or extraordinary in scientific papers. But the way that hydrogen interacts with metals is indeed quite remarkable and extraordinary. You can see some examples here. So this is, ductility, uniaxial stress-strain curves. You can see that if you expose your metals to hydrogen, for example, exposing them to hydrogen gas, then you get a very significant reduction in ductility. Even more significant is the effect on fracture toughness. You see here in the center. This is for a pressure vessel steel. You can see that 6 parts per million of hydrogen, a tiny amount of hydrogen, is sufficient to bring down the toughness of a pressure vessel steel from above 200 megapascals per meter to below 20 megapascals per meter. So an order of magnitude drop, going from a very ductile metal to almost an engineering ceramic. And the same goes for fatigue. These are fatigue curve growth rates versus stress intensity factor range. This is in air pipeline steels, in air and in the presence of hydrogen gas. You can see this is a log-log plot, at least 1 order of magnitude increase in fatigue curve growth rates whenever you expose those pipeline steels to hydrogen. So this is, of course, a problem because we need to develop this hydrogen energy infrastructure. This doesn't exist at the moment. Yet the materials that we want to use for that hydrogen energy infrastructure are going to be very susceptible to the presence of hydrogen. And it's a problem because we want to be able to predict these things quickly. We want to be able to understand under what are safe regimes of operation. So that's an opportunity for models. And of course, the fact that metals are so sensitive to hydrogen is a problem, and it has been a problem for a very long time, particularly in oil and gas and quite aggressive environments. Now, with the development of high-strength steels, like the ones we heard in the previous talk, then we are seeing more susceptibility to hydrogen embrittlement, and therefore this problem is expanding to other applications and sectors. For example, civil engineering, construction, and so on, even automotive industry as well. Whenever you're using high-strength steels, you're going to have hydrogen problems. Because again, hydrogen is everywhere. You can have hydrogen coming from the humidity, from the manufacturing process, and so on and so forth. And of course, this is going to be a problem for what I discussed before. We need to deploy a hydrogen energy infrastructure, and accidents are going to happen. In fact, this is very early days of the technology. Very few countries have started to develop a hydrogen energy infrastructure, and those who are doing it, like Norway, have seen already accidents as a result of hydrogen embrittlement. So a lot of questions come to mind. You see here this newspaper article in the UK. It was from last year. They were hoping to have hydrogen gas in the natural gas pipelines. They have decided to wait 1 more year to fully understand under what conditions will those pipelines fail, under what conditions we can safely transport hydrogen. And again, this is an opportunity for modelers because we really need to make decisions quick, and we need to map a very wide range of situations, and the situations that are not easy to test in a lab. This is full-scale engineering testing in a way. So it's also a big challenge for modelers, an opportunity and a challenge in that we need models to urgently map safe regimes of operation to understand under what conditions we can transport and store hydrogen. But at the same time, we don't have the luxury to be able to calibrate our models with experiments. We need to be very confident in our models because we need to be able to predict things full scale without any sort of calibration or validation. So we tried to address that challenge in my group, and we did so by, as I'll explain in a minute, trying to be as mechanistic as possible, trying to resolve the underlying physics as explicitly as we could. So I'll start by telling you a little bit of that modeling framework, which addresses each of the stages involved in hydrogen embrittlement. I'll then show some representative results, and then I'll finish with 2 case studies that I hope will be of interest to you, which is, can we predict hydrogen-assisted fatigue? These are very expensive experiments, difficult to reproduce, and combine the complexity of both fatigue and hydrogen embrittlement. And also, can we determine, this is a very, both I would say scientific and technological question, can we determine what are safe regimes of operation to transport hydrogen in existing natural gas pipelines? So let me start by describing the modeling. So the model has multiple ingredients, and I'll describe them based on the different stages. So whenever we want to understand hydrogen embrittlement, we need to understand the uptake of hydrogen in the metal, how much hydrogen is coming in, the transport of hydrogen within the metal, how it's structured in the microstructure, and then finally the embrittlement process per se, how the hydrogen nucleates and grows cracks inside of the metal. And the philosophy that we try to take here is that in order to be able to predict those full-scale engineering problems, we cannot rely on parameters that need calibration because we won't have the luxury to calibrate. So we try to maximize physics and minimize assumption and parameters. At the end of the day, in an ideal world, we want to have a model that relies purely on material properties that we understand that we can independently measure, like Young's modulus, strain hardening exponent, diffusivity. Those things we like. We don't like alpha, beta parameters that need some calibration. So let me tell you a little bit of how we do this. So first we go to hydrogen uptake. Here the goal is for a given environment, quantify what is the hydrogen that you have here in the subsurface of your metal, how much hydrogen is coming in. And this is difficult because hydrogen comes from multiple sources, through forming, coating, plating, through exposure to any hydrogen containing molecule, through corrosion processes. Hydrogen can come from many places. I'll focus mainly on 2 scenarios. One, gaseous environment. This is the relevant to the energy applications whenever we have hydrogen gas coming in, or an aqueous electrolyte, the situation where you're exposing your metal maybe to seawater or any other aqueous electrolyte. For the case of the gaseous environment, the good news is that under steady state conditions, there's a closed form solution. This is what we call C-vertical. And that basically relates the characteristic of the environment, the hydrogen pressure is pH2. This is something that you know, that you pick as an engineer, to your hydrogen concentration in the lattice, in the subsurface of your material. So this is good, it's an analytical expression. The only thing I'd like to say here is that this depends on the solubility of your material, which you can measure with a permeation experiment, but it also depends on this exponential term, which has a hydrostatic stress term here. So I want to emphasize this because sometimes a lot of people in the community forget about the mechanics contribution, but the mechanics contribution can be quite strong. You cannot capture this when you do a permeation experiment. So one has to be very careful. Whenever you're doing a permeation experiment, you're going to measure a stress-free solubility, but where you care about is how much hydrogen is coming in when you have a pressure vessel with a crack. And when you have a pressure vessel with a crack, you have an exponential term with a hydrostatic stress. And the hydrostatic stress, of course, is going to be very large near cracks. So the mechanics contribution is important and one should not be important. But anyway, that's good news. This is a closed form solution. If I know my solubility, if my finite element tells me what is my hydrostatic stress, I know my pressure, I know my hydrogen concentration. When we have aqueous electrolytes, the picture is much more complicated, and is of interest also for the energy application to understand the correlation between gaseous and aqueous electrolytes, because we are trying to use historical data. Running experiments on hydrogen gas is quite complicated and expensive and a health and safety challenge. But running experiments with hydrogen comes from the aqueous electrolyte is much easier, and we have decades of experimental data from there. So we're trying to correlate both. But it's difficult because for 2 reasons. One is that not only you need to resolve the surface reactions, but you also need to resolve the electrochemistry of the electrolyte. Because we know from, as anyone in the corrosion community will tell you, the conditions of the electrolyte in the bottom, where an engineer can measure them, are very different to those inside of occluded electrochemistry, such as cracks or defects. So that's a challenge. I mean, the good news is that we know how to express mathematically, I would say from mesoscale first principles, what happens there. So we have Planck equations, and using the equations depend on diffusivity, on Faraday's constant temperature, physical quantities, and then you can also resolve the hydrogen evolution and absorption reactions. So overharvest and absorption reactions that are happening in the crack tip. So you can express this mathematically, you can implement this into your finite element code, and then you have a boundary value problem that looks like this, where you have an electrolyte where you're solving for as many ionic species as you need. Then you have a metal, which may contain a defect, where you're solving for your mechanical problem, for the hydrogen transfer problem, and then you're solving for some interface reactions in between. And all of these are degrees of freedom, and back in the day or 10 years ago, it was difficult to solve a problem with 10, 15 degrees of freedom per node, but now we can do those things much more conveniently. And we've also done quite a lot of work on trying to accelerate those calculations with lump integration schemes that I won't have time to discuss. Anyway, once you solve a system, this is what you end up with. So you have this is a typical quantity. You solve, for example, pH inside of the electrolyte. You can see that it changes quite dramatically inside of the crack to the outside of the crack, as you would expect. And then you can predict, the hydrogen uptake as a function of the time, as a function of your material, as a function of the fluid flow, as a function of applied potential, and so on. This is just a representative result. But I guess that the end point is that for whatever environment you have, you're able to quantify hydrogen uptake. And then you can correlate that with Sept flow, and you can also quantify how your electrochemical experiment gives you something that is similar to your hydrogen gas condition. Okay, so that's on the hydrogen uptake. So in theory, we have at least a method that is to a certain extent accurate in predicting hydrogen uptake. Now, once the hydrogen is inside of the metal, the question becomes, okay, well, how does hydrogen distribute within the component and within the microstructure? And well, if we think of just hydrogen transport, it's relatively straightforward. It's described by an extension of Fick's law. So hydrogen is driven by gradients of concentration, and also gradients of the hydrogen stress. And again, strong coupling with mechanics. This is a very important problem, mechanical problem. So you can see, in fact, if you solve this equation for the steady state condition, you end up with a situation where the hydrogen concentration depends on an exponential term, where again you have the hydrostatic stress. So the hydrogen concentration is going to be very high near cracks and other stress concentrators. And this is only part of the picture. Hydrogen not only travels freely through the crystal lattice, it's also sequestered. Well, basically, let me say, if you solve this equation, this straightforward equation, a couple chemo-mechanical problem, you solve that in your finite element model, and you get something like this. So this is distributions of hydrogen concentration, and this is, for example, a pipeline with a weld. You can see how as you increase your pressure, the hydrogen diffuses through the weld, and you can do that also with microstructure scale. So this is relatively well understood. The other thing is that hydrogen not only travels freely through the crystal lattice, it's also sequestered or trapped on microstructural defects, grain boundaries, carbides, dislocations. So you need to come up with a theory that's able to encapsulate that, and we work with other people on multi-trap theories based on Oriani or Wagner-Foster, where you basically incorporate the effect of each of those traps through binding energies that quantify how energetically favorable it is for the hydrogen to sit in those places. And I'm not going to spend too much time on this, but one thing that I should say is that one aspect that I think the community has overlooked is the fact that if you're interested in knowing how much hydrogen you have in your dislocation field, you not only care about the statistically stored dislocations, but you must also take into consideration GNDs, geometrically necessary dislocations. We heard in the previous talk about the importance of GNDs, and these are very important in hydrogen because GNDs, due to plastic strain gradients, they dominate near cracks and inclusions, and we can see this experimentally. And they play a big role in hydrogen, not only if you want to quantify how much hydrogen you have in your dislocations, but also because, as we heard in the previous talk, GNDs play a big role in the strengthening and hardening methods. So we know that GNDs will act as obstacles to other dislocations, and that elevates stresses. And this is something that people have seen through a wide range of microscale experiments. And the implications in fracture mechanics is that if you look at your stress inside of your crack, what you see is that far away from your crack, basically you can capture these GND effects through appropriate constitutive models, like strain gradient plasticity. And what you see is that far away from the crack tip, these GND effects are small, you can neglect them. But near the crack tip, because you have very high plastic strain gradients, these GND effects are going to be big, and therefore your stresses are going to be much larger than those that you can predict using conventional theories like von Mises. And this is very important in hydrogen because, taking you back to this equation, we have an exponential term that relies on the hydrostatic stress. So you can see here that the hydrogen concentration is going to be much, much higher near the crack tip. And as you will see later, this is important in order to rationalize the underlying physical mechanisms that drive hydrogen. And in fact, we have seen when we run simulations combining these, couple chemo-mechanical models that account for the GND effects, for these strain gradient plasticity effects, and this is the only way that we can get a good agreement with experiments. It's difficult to measure hydrogen concentration ahead of the crack, but some people have done it. And you can see here that only by accounting for these GMD effects, we're able to capture these very high hydrogen concentrations that experiments predict near crack tips. Okay, so now we are moving to the embrittlement part. So we know where the hydrogen is distributed within the component, and we also know where the hydrogen is distributed within the macrostructure, relies on those binding energies that I told you before. So now what happens with the cracking process? And here, I think one of the challenges is, there's two types of challenges in trying to predict when hydrogen embrittlement occurs. One is a physical challenge, so what is actually hydrogen doing that facilitates the nucleation and growth of cracks? And the other one is the computational challenge. How are we going to couple this evolution of cracks through a component computation, right? These are interfaces, these are discontinuities. And for that, we use these facial models that have been used in many science and engineering problems. The idea is quite simple. You overcome all the mathematical and computational challenges that come with tracking discontinuous interfaces by smearing that interface over a finite domain and using an auxiliary variable, the phase field, to tell you where the interface lies. So then the phase field will take a distinct value in each of the phases. It will be 0 maybe in the blue phase, 1 in the red phase, and it will vary smoothly in between. And then if you define a suitable differential equation for the evolution of this phase field, then you're able to capture interfacial problems of arbitrary complexity. And it's very convenient, this implicit representation of interfaces also for fracture problems, because you're defining basically your fracture equation, your interface equation in the entire domain. So there's no need for any special treatment. Topological changes such as divisions or merging of interfaces like crack coalescence, crack branching, those are naturally captured without any ad hoc material. And then finally, it's very well suited for multiphysics problems because you can combine this crack equation with any other equation that you're interested in, hydrogen transport, uptake, whatever you care about. And I mean, facial modeling, as I used to say, has really been a revolution in many areas of science and engineering. It all started in microstructural evolution, what is now by far the most widely used technique to simulate solidification. We're interested in its application to fracture mechanics, but again, it's becoming very quickly the dominant technique. And you can see why here, this is the outcome of the simulation. This is a hydraulic fracture process. That's why you see such a funny crack branching process. You can see that the model is able to capture very complicated stuff, branching, nucleation of secondary cracks, coalescence of multiple cracks. And also recently, for I won't have time to discuss it today, we have shown that the phase field paradigm can be used to simulate corrosion. You can use the phase field to track the evolution of the corrosion front, to track the interface between the aqueous electrolyte, the seawater, and the metal, for example, right? The evolution of this electrolyte metal interface. But I'm going to focus today on fracture. And I think, again, going back to what I said before, the two aspects that are challenging in this problem is first, mathematically, it's difficult to predict cracks. And now it seems that we have a tool that finally allows us to do so. But the other one is that, the method has to be physically sound. These nice colors need to correspond to reality. And I think the phase field is a nice platform for that because it basically allows you to incorporate Griffith's energy balance. So this goes back to the foundation of fracture mechanics, thermodynamics of fracture. For a crack to grow, the energy stored in the material has to be equal or larger than the energy required to create tuner surfaces, the fracture energy, the critical energy release rate. And you can express this into a variational form. And then if you're able to minimize this functional, then you're able to predict the evolution of cracks as an exchange between the stored energy and the fracture energy. But this is tricky because you don't know where your crack lies. So here's where you make use of a phase field to enable the regularization of this functional and be able to predict the evolution of cracks. Again, as an exchange between fracture energy and stored energy in agreement with thermodynamics. And basically, you can see the phase field is a little bit like a damage variable. So you go from 0 in in-time material points to 1 in fully cracked material points. It's a little like a non-local continuous damage mechanic model. There's some length scale in there, which makes it mesh objective. Your results are going to be mesh independent if your mesh is fine enough. And then you also degrade like a damage variable, the low current capacity of material. And you can get a good overview if you look at the balance equations here. So on the top, you have the balance of linear momentum. So this is the standard equation that you solve in the formation problems with the phase field degrading your low current capacity. And then you have another equation that is the equation that describes the evolution of this phase field. And this is basically a competition between the energy stored in the material, which depends on mechanical straining, and the fracture energy, the toughness, a material property that we can easily measure. And just by solving this differential equation, again, you can see here, you can capture very complicated cracking patterns on the original finite element mesh and without any convergence problems. The method is very robust. And again, I won't have time to discuss the numerics, but there's a lot of work going on there. They don't take quasi-quantum schemes that make it very robust. Here you see, by the way, crack branching due to the application of a dynamic load. By the way, I'm going to use always red color to denote cracks and blue color to denote intermediate. And this slide overviews a little bit of why the phase has become so popular in the fracture mechanics community. You can see here for a wide range of materials, this is metals, ceramics, composites, functional green materials. Not only that the method is able to capture very complicated cracking patterns, but that is able to do so showing a remarkable agreement with experiments. You can see here, it's quite a remarkable agreement with experiments. So this is the takeaway. The method, in my opinion, is physically sound and is computationally very robust. So I think we're well equipped. And now we try to extend this to hydrogen enrichment. We did this some years ago, and we thought, okay, if I try to develop the easiest phase field model for hydrogen enrichment, then I have a three-field problem. I have the mechanical problem, I have the hydrogen transfer problem, and then I have the damage problem. And you can see that they are coupled, and I'm highlighting here some of the couplings. But the most important coupling is, of course, how hydrogen degrades your fracture energy. How does hydrogen embrittle metals? And there's many ways you can do that. Of course, we know from experiments that this is the case. We have shown you before, I showed you some data. This is pipeline steels. You can see how as you increase your hydrogen pressure or your hydrogen content, your fracture toughness goes down. So there is some experimental evidence. Also, there's plenty of experimental evidence. So you can use that experimental evidence to fit that toughness value. And this is a lot of what industry or industry collaborators do. They have a lot of toughness versus hydrogen concentration data. So they can just feed the data and input that as a function. But of course, at the end of the day, what we want is to be able to develop a mechanistic model, purely mechanistic model, that is able to capture the physics of the underlying process. And the good thing is that the framework is universal, as you say. So any mechanistic interpretation, you have a fatigue hydrogen degradation function that you can make it dependent on any macro or micro mechanical variable that you might be interested in. So I've seen that a lot of groups have taken this framework and extended to different physical interpretations of hydrogen. And let me tell you what I think is happening. So if you were to develop a mechanistic degradation function for hydrogen enrichment, the key question to answer is how does hydrogen make metal break? How can it be that the same material in the absence of hydrogen fails in a very ductile fashion through those micro void growth and coalescence mechanisms, and the moment you bring hydrogen into the picture, it fails in a very brittle way through, as you see here, intergranular cracking mechanisms. So what is happening between here? In my opinion, in summary, there's three key ideas to understand this. The first one is that when you look at the problem at atomic scale, for example, we're running DFT calculations, you can see that the surface energy or the fracture energy of your metal is very significantly degraded with hydrogen. So this is surface energy versus hydrogen occupancy for nickel. These are DFT calculations for two types of grain boundaries in nickel. And you can see that if your grain boundary happens to be full of hydrogen, an occupancy of 1, then you're reducing your fracture energy by 40%. So now the next question becomes, okay, this seems like a possible scenario. If my grain boundary is full of hydrogen, it's going to be much weaker. But how much hydrogen is actually in my grain boundary? Because if I'm somewhere here, then well, this is a secondary effect. And the answer to that comes from the chemistry, I said before, of thermodynamics. I said before, how likely this hydrogen to go to a certain microstructural defect depends on that binding energy. And we can measure that experimentally. And we know that for grain boundaries, which are strong traps, we have binding energies of -40 or smaller, then we are somewhere here. And here you can see basically a plot of Oriani's equilibrium where you see trap occupancy. Yellow means fully occupied, blue means empty. This is the lattice hydrogen concentration, and this is the binding energy. So for grain boundary, we're somewhere here. And you can see that for typical hydrogen concentrations like 1 ppm, then your grain boundary is essentially full. Even 0.1 ppm, your grain boundary is almost full. So it is energetically favorable for the hydrogen to sit in those grain boundaries, to accumulate in those defects. And we have seen in atomistics that when we do that, we have a 40% reduction of the binding energy, of the grain boundary strength. So then the last question is, okay, what happens? Can you actually go from micro-void cracking mechanisms to brittle mechanisms just by lowering 30 to 40% your grain boundary strength? And this is tricky because the grain boundary strength is 10 times the yield stress or so, right? So if you bring it to 6-7 times the yield stress, it still is quite a high value. But what we see is that when we account for those GMD effects that I mentioned before, for those plastic strain gradients, your hydrogen content is big enough and your stresses are big enough that this cleavage strength that you don't reach normally in the absence of hydrogen, hence why you need the ductile micro-void mechanisms, is lowered, your stresses cross, these two lines cross, and then you have storage. You have a model that just by running offline one atomistic simulation without any fitting coefficients is able to predict naturally the shift from ductile to brittle. And this is straightforward to incorporate into this phasal models because we are solving a hydrogen transport problem. So we know the hydrogen concentration. Through thermodynamics of trapping, we can relate that to the hydrogen occupancy in the different microstructures in our critical interfaces. And then we just come to atomistics with whatever coverage you have, and we reduce our fracture energy that comes into the phasal equation. So it's very straightforward to incorporate this. Okay, so let me just tell you some examples of how this model works. So first, I'm going to show some results here. These are some representative comparison of the experiments. These are pre-charged steel bars. I think it's double stainless steel. No, these are high-strength steels. And you can see that they measure basically the notch strength versus the hydrogen content. And again, you can see that the symbols are the experiments, and you can see that the phasal model seems to deliver a good agreement across a very wide range of hydrogen concentrations. These are another set of experiments done in Norway. Here, what they have is duplex stainless steels. They are subjected to a constant load and immersed in a seawater bath. And then what they do is they introduce hydrogen to these cathodic reactions, and then they apply the constant load and quantify the time to failure. Each of those samples is loaded at a different load, so they were hoping that one of them was loaded at a load that was small enough not to see a brittle. That did not happen. As you can see here, the symbols of experiments, all of them failed relatively early for engineer standards, but we can take the model and not only reproduce the experiments, but also run large-scale simulations over large time scales and predict what is this embrittlement region, this load below which you will not see embrittlement. So again, at the end of the day, this is a, I would say, multi-scale informed, but at the end, macroscopic continuum model. So it's easy to run those kind of large-scale simulations. And this is something that we have exploited to kind of bring this idea of virtual testing to the hydrogen energy sector. Because again, with this continuum like fundamental models, we can solve problems of any dimension and choice. And these are some 3D problems that we have shown here. In fact, we can also create some sort of digital twins of critical infrastructure. For example, what you see here is a pipeline that contains hundreds of defects which repeat corrosion. All of those red dots are defects. We can incorporate easily into our fundamental model those defects because we are solving for the phase field as a degree of freedom. So you can just initialize your phase field equal to 1, and then you can simulate what happens, and you can subject that pipeline to in-service conditions, and you can see how those defects are growing, how they merge with each other, and how eventually you get the complete failure of the pipeline. So I guess the takeaway that I want to say is that we have, I would say, as physically as we can at the continuum level, physically informed model that is able to predict hydrogen-assisted failures at scales and conditions relevant to engineering practice. So no matter what is the complexity of your problem, at the component level, you can predict fracture through this combination of electro-chemo-mechanical models. And we have also extended this to fatigue. So there's a growing area of facing fatigue, where the idea is that you have a fatigue degradation function. So not only you degrade the toughness of your material through hydrogen, but you have a variable that accumulates with your cycle loading that degrades your fracture toughness. And when you do that, you see that basically the price to pay is that you need to add 2 parameters to your model that quantify how susceptible your material is to cyclic load, basically to cyclic damage. And when you do that, you can see that we can capture SN curves with and without hydrogen with, I would say, relatively good agreement. And then you can also obtain as an output of the model the Paris law behavior. So we don't tell the Paris law behavior as an input to the model. The model tells you what are the Paris law constants as a function of the environment or anything you're interested in. And you can also compute virtual SN curves for any arbitrary choice of environment and geometry, his and notch component, and applied load and his load history. And these, by the way, as you say, these are cycle by cycle calculations, which are very powerful because then you don't have to apply superposition. You cannot apply superposition when you have hydrogen. But at the same time, they're computationally heavy. And again, a lot of work is going on accelerating those calculations. But now we're able to do millions of cycles on 3D. So I think we're getting to a point where we can handle large scale problems. So let me just finish with these 2 case studies that I hope will be of interest to you. The first one is related to hydrogen-assisted fatigue. So a lot of these applications in energy, of course, involve components that are going to be subjected not only to hydrogen gas, but to cyclic loads. Most of them, most engineering components are subjected to cyclic loads. And identifying the behavior of metals under hydrogen and cyclic loads is quite challenging. So these are experiments conducted by Sandia, fatigue crack growth rates. These are done in Sandia National Labs. So you can see they have data for different hydrogen pressures, up to 100 megapascal of hydrogen pressure, and different load ratios and different frequencies. And this data is very, very valuable. This is what engineers are using these days to design hydrogen energy infrastructure. But it's also very difficult to get. There's only, I would say, 5 labs in the entire world who are able to run experiments at these pressures and cyclic load. So it's expensive and very difficult to get. There's quite a challenge to run experiments at 100 megapascals of hydrogen pressure. And this data has some issues as well. That's why industry partners approach with this. One issue is that there's a frequency effect. Normally in fatigue, we don't care about frequency. But the moment you have hydrogen, if you load very slowly, there's more time for the hydrogen to accumulate. But if you load very fast, then the hydrogen doesn't have time to move. So there's a frequency effect. And we know that the slower we load, the more susceptible we're going to be to hydrogen embrittlement. So you want to run your experiments in the frequency of your application. But the application involves very low frequencies, and these experiments are very expensive, so we run them at high frequencies. So we're being non-conservative, and the industry is worried, okay, what is the error that we're making by running experiments at very high frequency? The other problem is that each of these curves is tied to the test condition, right? Each curve is valid for a given material, a given frequency, a given load ratio, a given hydrogen pressure, and these tests are expensive. So we want to be able to have a tool that allows us to interpolate between the data and extrapolate beyond the data. And then, of course, we need estimates for arbitrary loading histories. This is for a constant applied range. And also, we are disregarding the crack initiation stage, and we need tools that are able to predict crack initiation. So we did an interesting study with an industrial partner, where they basically released the data to us a little bit, little by little. So they said, okay, you guys claim to have a model that is able to predict things. So let's see how far you can get. So first we said, okay, we understand that you have a phase field fatigue model that relies on 2 parameters that you don't fully understand. These 2 parameters, I must confess, this is a growing field. We know they quantify the susceptibility to cyclic damage of a material, but I don't know very well what they mean. It's not like Young's model. So they said, okay, we're going to give you the data in air. This is for a pressure vessel steel. And I'm going to let you fit those 2 parameters. So we run our virtual experiment. This is my compact tension virtual experiment. I see my crack growth. And of course, I get an excellent agreement with experiments because I'm fitting those 2 parameters. There's no hydrogen here. I'm just fitting those 2 parameters. Okay, so now there's no more fitting. Now this is that we have some hydrogen data at 55 megapascals. We can use that Sept flow that I showed you before. We convert 55 megapascals into a right concentration. We impose that as a boundary condition. We do not touch anything in our model. We don't define, we don't recalibrate anything. We do not change any of the parameters, and we run the simulation. And this is what came out of the simulation. So we were quite happy. And then they said, oh, we also have data at 106 megapascals. So please run a simulation at 106 megapascals. Again, you're not allowed to touch anything. You're not allowed to recalibrate anything. The only thing you do is you change your boundary condition. We know from Sept's law what is the concentration that is associated with 106 megapascals. We put it in there. We send in our simulation. We put it together. And this is how it looks like. So we're well happy about it. They also have data for different load ratios. So again, they said, no touching, no recalibration. You're only allowed to change the way you load your sample. We did that. This came out of the model. Again, I think a good agreement across the board for engineering perspectives. They have data for different load ratios and different pressures, 55, also 106. Again, not touching anything, changing the pressure, changing the load ratio. This came out of the model. And they also have data for different frequencies. Again, we just change the way we load our sample. We do not touch any of the parameters involved. This came out of the model. And this is for a given load ratio. They have for a different load ratio. And again, a good agreement. All the data that we threw to the model was able to blindly predict without any recalibration whatsoever. So we were quite happy about this. I must confess, I wasn't expecting such a good level of agreement. And now we use the model to try to understand things. So one of the problems with these experiments is that because they're expensive and they take time, they do not expose the sample to hydrogen and then do the mechanical test. They do both at the same time. And this is a problem because in practical applications, pressure vessels, pipelines, they're going to be exposed to hydrogen for a long time. So we can do that easily in our model. So we just expose our compactation sample to hydrogen. We let the hydrogen redistribute to the model. And then once it's completely uniformly distributed, then we run our virtual test experiment. And what we see is that you get an elevation of 2.5 times fatigue crack growth rate. So it's up to you as an engineer to decide whether this is a big change or a small change. Then the other thing, of course, we were very interested in is in changing the frequency. In the real application, we work at very low frequencies, but experiments are done at high frequencies. So we are able to do that with the model, and sometimes they run experiments at low frequencies. So we were able to actually show that the model agrees quite well with experiments at low frequencies, and we were able to predict what happens in the regime where they're going to basically be running their pipelines and pressure vessels. And last but not least, there's some experiments done in Japan on full-scale test when you have the full pressure vessel that fails after tens of thousands of cycles or thousands of cycles. And we were able, they did for 2 types of alloys and 2 types of notches. And again, you can see the model is able to predict very nicely or in good agreement with experiments the behavior of a full-scale component over thousands of cycles. So I think this is a good sign that the model is mature enough to be applied to engineering practice. And then the last thing that I want to discuss, the last case study, is the pipeline one that we discussed also yesterday. So there's big ambitions. This is what they call a European hydrogen backbone. All governments around the world are hoping to transport hydrogen in natural gas pipelines. It will be much cheaper than to build dedicated pipelines. However, this is a challenge because those pipelines have been there for decades, and they contain a wide range of defects. And because those pipeline steels are very sensitive to hydrogen. So here you see the hydrogen fracture toughness. You see here fracture toughness. So pipeline steels X52, X80, they have toughnesses that are above 200 megapascals per meter. But the moment you bring hydrogen to the picture, you see 0.5 ppm, very small amounts. You're talking about 40 megapascals, 50 megapascals per meter. So not as brittle as a ceramic, but quite brittle. These are again experiments here that correspond to that hydrogen situation. So these are the pressures that they transport natural gas these days, or the pressures that are hoping to transport hydrogen. The higher the pressure, the stronger the economic case for using hydrogen as clean energy vector. So we need to understand basically under what conditions can we transport hydrogen in natural gas pipe. And again, as you saw in the newspaper article, in the UK, they're hoping to make a decision next year on what will be the conditions that they can transport hydrogen. So under what conditions can we transport this? This is the key question. And this is a very difficult question to answer experimentally for multiple reasons. First of all, because those natural gas pipelines have been there for decades. So there's a quasi-infinite combination of pipe materials, weld materials. There's defects, pre-existing defects that have been there for operation over decades, from corrosion, from in-service conditions. And also as an engineer, you have a quasi-infinite combination of conditions as well. You can choose to transport your hydrogen at any pressure that you want, at any purity that you want. So there's many, many conditions, so it's very expensive to test in the lab. The other problem is that the weakest link are welds. Welds are going to be the weakest link of your material. And it's very difficult to test welds in a lab because, well, they contain residual stresses, as we discussed yesterday, but also the critical area is going to be the heat-affected zone, and it's not possible to extract samples that we can do fracture tests on the heat-affected zone. And then even when you do full-scale tests, and some people are doing pipelines, it's a bit challenging because you have a nitric oxide layer that might not be disrupted, and that prevents hydrogen uptake, and that might not be disrupted during the duration of the full-scale test, but will be disrupted over the decades that you're operating. So models seem to be useful here, and in order to answer that question, basically we create a framework where we combine those phase field models for hydrogen and bitumen that I've showed before with welding process models. So you simulate the welding process, then it gives you a property distribution within your weld, the different phases, the different heterogeneities that you have in there. It gives you residual stresses, and then you run the simulations with increasing pressure and predict when the patterns will fail. So the first step is something that is new to us. We haven't worked in weld process modeling before, but there seem to be plenty of good models out there from the nuclear community mostly, and we were actually quite impressed with the way they work. Even though they are simplifying a very complex process, they seem to be working quite well. So here what you see is a girth weld, multiple passes, and this is a seam weld where you have a couple of passes, and you're able to predict, the phase volume fraction, and you're able to predict, of course, residual stresses. And you see here, this is, the different phase volume, austenite, bitenite, and so on. So depending on your cooling rate, depending on your welding process, of course, you get a distribution of different phase fractions. And if you have different phase fractions, then you're able to predict different hardness levels. And you can validate them with experiments. So this is, again, collaboration with industry. They'll tell us, this is how we did the weld, do it in the computer, and then let's look at the hardness maps. They did hardness tests. Let's look at the hardness maps, and that will give us an indication of the microstructural heterogeneity that we have. And you can see, this is the same scale. It's not identical, but it was far better than I expected, given the complexity of these processes. So that gave us some confidence in the model. We also predicted residual stresses, and again, it's not easy to measure residual stresses, but you can see that this is X-ray diffraction, I think. This is the experiment, this is the model, again, the same legend. And it doesn't look too bad. And we were actually quite happy with the level of agreement. So we are trusting these weld process models that we took from the literature. We didn't develop ourselves. But this is good because that allows us to predict the variation in properties within the weld. So you see here, this is a seam weld, and you can see here how the toughness is degraded in this heat-affected zone. So this is the problem, basically. We have, and you can see in the hardness maps, we have regions that are very hard and brittle in our pipelines, and these are the regions that are going to fail first. So if you're quantifying your hydrogen enrichment of your base metal, that's not gonna be the weakest link. That's not gonna be what fails first. You need to worry about that. So, but we can able to incorporate that macrostructure heterogeneity in the model, and then basically we expose the pipeline to a hydrogen concentration, and we see where things fail. This is what you see here. So this is the well and the pipe. At the bottom, you see the phase field. At the top, you see the hydrogen concentration. We're increasing progressively our pressure, 100% pure hydrogen, and we're seeing when a crack will develop. And then eventually, as you see, pop, a crack pops out, and your pipeline has failed. So this is good because then we can test any wide range of conditions. So, for example, we went to the welding standards, and the welding standards will let you pass your weld with certain defects, some admissible defects. So we incorporated all those admissible defects that we know exist in those natural gas pipelines because the standards allow for it, and we quantify whether they were problematic in hydrogen or not. And this is something, once you have a model, it's very easy to do, right? You put whatever defect you want, you run the simulation, and you see what you get out. And I don't have time to go through the details, but we learned a number of things. What we learn is, first of all, that defects matter significantly. So as you expect, residual stresses also matter significantly, and macrostructural heterogeneity matters. This is something that wasn't 100% clear, but it seems to be clear. And what we found quite interesting is that when you have a critical defect of 3 millimeters along a hard heat-affected zone, which is something that we have seen on pipelines, natural gas pipelines taken out of service, your failure pressure could be as low as 15 megapascals. And this is problematic because 15 megapascals is one of the numbers that are being discussed in the industry to transport hydrogen. And what I find quite interesting is that we published that paper last year, but a few months after we published the paper, they ran a full-scale experiment on a real pipe where they introduced a small notch, a 3 millimeter notch along the heat-affected zone in a weld, and they saw a failure pressure of 12 megapascals. So it seems that the model running months before under slightly different conditions was not too far away from the practical case. And then before I finish, I would just say that thinking a little bit on the future, I don't know if this thing is running. Yeah, thinking a little bit about the future. I was hoping to present a little of this today, but it's still very much ongoing work. Sometimes people ask me, okay, what's going to be the future looking like? And I think you'll notice that so far we haven't looked that much into the microstructure. And the reason being is that a lot of these applications involve, if you think of oil and gas, traditionally hydrogen has always been a problem for very aggressive environments. Situations where you already have deep defects to start with. So you didn't really care about the microstructure. However, now with the push, particularly for hydrogen aviation, 2 new problems come into our plate. One is the microstructure. We're going to deal with very clean alloys, where what matters is the initiation of fatigue cracks, which is very microstructural dominated. So we're going to have to take these tools to the microstructure. And these are some representative examples of what we're doing these days. So you can extend, these are continuum level tools. You can use them with crystal plasticity. You can use them with new theories that we have to capture segregation to grain boundaries and cracking. So they're suitable for those type of problems, at least, CPV type of calculations. And the other problem that, again, I didn't want to show some data today, but still very much ongoing, is that we're going to be, everything that I showed you before was isothermal. We only care about hydrogen and isothermal conditions, which are typically the worst. But now, due to the application in aviation, we're going to go to very low temperatures, which are related to hydrogen storage as liquid hydrogen, and very high temperatures, because they're going to burn hydrogen in the engines. So again, all the complications that you have in the superalloys, the high temperature, the demanding conditions of engines, now you need to add the hydrogen there. So I foresee a lot of interest. I know the local group here is doing good work in this sense. I foresee a lot of interest into combining these tools with, again, microstructure, with crystal plasticity, and so on, and thermomechanics. So just to finish, I would just say that I think that these phase field ideas and multiphysics modeling can be combined to develop mechanistic tools that allow you to resolve the mesoscale physical processes as they happen in reality, and that allows you to minimize assumptions and to deliver predictions based on parameters that we know quite well: diffusivity, toughness, stress-strain curve behavior of the material, and so on. I think that the framework is quite general, so I know there's a lot of people out there that disagree on my interpretation of what hydrogen enrichment is, but they can also take the framework and implement whatever they think is happening in hydrogen enrichment, and people have done that. And you can also combine it with, microstructure simulations, wells, stress corrosion cracking. It's a very general framework in that sense. And the beauty of being a continuum level framework is that, well, maybe you don't get as much insight as slower scale simulations, but you are able to take this to the practical case. You can do virtual testing on hydrogen containing environments. And in fact, as I've shown you before, these models are now being used to design pressure vessels for hydrogen storage, and also to make decisions to determine under what conditions will be safe to transport in the UK hydrogen in natural gas pipelines. That's all. The last thing I would say is that all the codes that we developed, they're all made freely available. We work with some commercial packages like Abacus and Consul. Consul last hydrogen model is based on our paper, but we also use in-house codes in C++, MATLAB, Julia, Phoenix, and so on. And they're all made available. So all the results I showed you today, you can reproduce at home. That's all. Thank you very much for your attention. Thank you.